Welcome to part 5 of the recursion video series. So in my last video I said we'll start with decision trees, but then I thought maybe I want to cover this also, and here there is a tree which is similar to a decision tree but not quite, but I'll get to it. So as you might already know, Fibonacci sequence is a sequence like this, basically not like this, exactly this. So the first two elements are 0 and 1, and every element is the sum of the previous two. So this one is 0 plus 1, 1. This one is 1 plus 1, 2. This one is 2 plus 1, 3. This one is 3 plus 2, 5. So if you watched my previous videos, you would remember what I said is recursive solutions lend themselves very well when you're solving the same problem again and again with different input. So which is the case here, right? So if so this is the index. So if you want the Fibonacci at index 4, you're doing 3 plus 2, right? So it's the same thing you're doing, but a different input. So the input here is 2 and 1. What if you had Fibonacci at 3? You're doing Fibonacci of index at 2 and index at 1, which is this plus this. So at every point, you're doing the same thing. You're adding two numbers. So this is an ideal place for using a recursive solution, where you're solving the same problem again and again for different input until you reach the base case. For base case, it's different. So this is the base case. For 0, Fibonacci is 0. For 1, Fibonacci is 1. But until the base case, every single one, if you can know the two Fibonacci of the previous numbers, you just add it up. So this is the code, the recursive code. Just a disclaimer, I haven't added memoization here. Memoization is something where you store previous results to reduce the number of computations you need to do. So in the description below, I'll have the code with memoization, but this is to keep it simple, just the recursion part of it. So here, what we're doing is, if I equal to 0 or I equal to 1, return I. This is our base case, which is these two. This is the indexes, the green. In the green, I have the indexes. In the orange, I have the Fibonacci numbers. So for index 0 and index 1, for 0 it's 0, for 1 it's 1. So that's why I said for 0 and 1, just return I, because it's same as the index. After that, for any number further, you do Fibonacci of I minus 1 plus I minus 2. And you keep doing this thing until you reach base case, and base case you return this. So let's look at this tree. This makes it easier to understand. So this is like a decision tree, but not a decision tree. Decision tree in strict terms is where you make an or choice. You have to do this or this or this. But in this case, we are doing both. So that's why I would hesitate to call it a decision tree. But if you want, for practical purposes, it doesn't make a difference. Basically, it's the way you're thinking of the solution of the problem. And drawing a tree like this, actually, for majority of the complicated recursion problems, drawing a tree like this makes it much simpler. Before you write the code, you should draw a tree like this. So in this case, suppose this is the main calling code. I'm saying Fibonacci dot, this is the class name Fibonacci dot Fibonacci of 4. So this one calls here and passes in 4. So the input to this is 4. Now when you have 4, what happens? It comes here and it calculates of 3 and 2, which is this 3 and 2. For 3, again the same thing. It comes here, you'll have to calculate for 2 and for 1. 2 and for 1. For 2, you'll calculate 1 and 0. So any backtracking, or not any, but pretty much most of backtracking or recursion based problems, if you start off with this, you'll have a very good mental picture of what you want your code to do. And that makes it much easier to write the code. So this is how your decision tree, or if you want to call it decision tree will look like. Let's walk through this. When you want Fibonacci of 4, you'll calculate, so 4 comes in, you have 3 and 2, 3 and 2. When you have Fibonacci of 3, you want 2 and 1. When you have 1, you have 1 and 0. So 1 and 0, we already know the base case. For 1 is 1 and for 0 is 0. So this guy returns. Now this guy returns here, and then what this guy does is he adds these two. So 1 plus 0 is 1, he will return 1. Okay. Another thing actually, every single node in this decision tree is like a stack frame. Not like a stack frame, it is a stack frame. I will get to that later where we can walk through the stack frames, but for now let's just talk in terms of this tree. So this will add these two, return 1. This guy, base case, returns 1. What this node will do is once these two return, like he'll get this one and this one, he'll just add those two. So 1 plus 1, 2. This guy will return 2. Now on this side, base case 0, base case 1, return this. Once this guy gets both, so this is, like I said, this is every single node, you can think of it as a stack frame. So this stack frame, 2 is what was passed in. 2 passed in, it calls for 1, it calls for 0, gets both of them, adds them, returns it here. Okay, and now 1 plus 0 is 1, returns 1. Take another pen. Returns 1. Now 4, when 4 calls, it had called for 3, it had called for 2. It gets this for 3, this for 2, adds both, returns 3. Whoever is a caller, it returns 3, which is what it is, right? For index 4, Fibonacci is 3. So one observation to make here is when your code runs, it doesn't actually go this sequence. It doesn't do 3, 2 and do this simultaneously, because if you're not enabling multi-threading explicitly, the whole thing will run in one thread. So under normal circumstances, if you're not adding threading separately, this is how your code will run. When 4 calls, it will it will say this, but then it won't do this. It will come first, go through this path. So 4 calls, it comes 3. This is how your stack frames will look like. 3 will first call 2, 2 will first call 1. When this returns, only then it calls this. Then it returns, comes here, then 3 will call. So when we had come here initially, it needed 2 and 1, but it first went and explored this whole path, got the Fibonacci of 2, then it will go down this path, which is here. Then come here, this will return, and only after that this executes. And this executes, it comes here, returns, comes here, returns, comes here. I will get to the stack frame in a second. So this is how Fibonacci works without memoization. So memoization basically is, if you notice, I've already calculated fib of 2 here. So I don't need to calculate here again. So the memoization means you just store the previous result so that you don't have to calculate it again. So imagine your tree was much bigger. Now you go all the way here, come back, and then you don't have to calculate all of this again, right? You already can store the previous result and use that. So you can reduce the number of branches that you go out into, which means you can solve it with in lesser time, with lesser computation. So I'll have the code with memoization in the description below. So let's see how the stack frames work. So for that, let me rub out this part. So when your code starts executing, when main calls this thing, first you have the main. So main will have, so like I said, when your program starts, there is nothing in stack frame. When the main is called, there will be stack created for main, and this will just have that integer which is passed in, which is 4. You can just say index I equal to 4, and it will have a variable to hold the result, which will be int fib, which won't be populated until all of them return. So it will have this one that calls the fib function with value 4. That's the first call. So it will call with int I equal to 4. Then when that call is made, it checks the base case. Then it wants fib of I minus 1 and I minus 2. So first it will go in fib of I minus 1. Another stack frame is created for the next call where I equal to 3. When it comes to 3, it again makes 2 calls, 2 and 1. So another stack frame is created for I equal to 2. So we are going like this. When 2 comes, it again needs a stack frame for 1 and 0. It comes here, I equal to 1. So when it's 1, it will return 0. Okay. So it will return 0 and come back here. When it comes back here, this goes off the stack. So at this point, you know fib of I minus 1 equal to 1. But now you need to calculate I minus 2. So it will go this route. It will come again, another stack frame is created for I equal to 0. This will return 0, goes off the stack. This has I minus 1 equal to 1, fib of I minus 2 equal to 0. It will add both of these, return 1, goes off the stack. So fib of I minus 1 equal to 1 for this guy. Now this guy makes a call this way, where it passes I equal to 1. And then again, this guy will return 1. It will come here. It will go off the stack. Fib of I minus 2 will be 1. Okay. Now this guy will add these two and return up. So which is 2. 1 plus 1, 2. So it will return 2 there. So this guy will have fib of I minus 1 equal to 2. So now this only has calculated this side of the tree. Now it will calculate the other side. It will go start on this side. It makes another call to the method, which creates another stack frame with I equal to 2. When it comes here, again it makes another call to the method with I equal to 1, like this. This guy returns 1. So you know at this point in this stack frame, fib of I minus 1 equal to 1. Okay, but now it needs I minus 2, makes another method call, creates another stack frame, I equal to 0. Again, I equal to 0 will return 0. So this guy will know fib of I minus 2 equal to 0. Then it will add these two and return 1. So now we know fib of I minus 2 equal to 1. And then this will add these two, 2 and 1, fib of I minus 2 and I minus 1 and I minus 2, return 3. So then that comes here and equal to 3. And then once the program finishes execution, this also goes off the stack. So yeah, that pretty much covers Fibonacci sequence. Again, understanding the tree is very important. Before you solve, anytime you solve recursion or backtracking problems which involves multiple branches, draw out a tree, and also in your mind think about how the stack frames will work. This will call this and this, but then this will first call this, then come here, and so on and so forth. So by this video actually you have a pretty good understanding of like how to think of in terms of recursion and how to think of in terms of decision trees. But I will create a few more videos where I go into a little bit more involved examples. Alright, thank you.